So let's get it set up. So there's a couple things we've got to do. We're going to have to do a coordinate transformation because to describe this rotation, spherical coordinates is going to be the most straightforward. Okay. And so for now, we also recognize because this is particle on a ring, our particle is only moving in the x, y plane. So when I start to build up my Hamiltonian, right, for kinetic energy, because again, V equals 0, so we're only worried about kinetic energy. So that's negative h bar squared divided by 2m times the partial second derivative in x plus the partial second derivative in y. And this is the exact same thing that we did with the two-dimensional particle in a box. So here, this thing that I've got, this upside down triangle, so that's called del squared. Sometimes it's also called nabla. And sometimes it's also called the Laplacian. So all of these are names to describe this operator. And this operator is the partial second derivatives in multi-dimensions. And so we can have the two-dimensional del squared, or we can even have the three-dimensional del squared that would include the plus z dimension. Okay, so we're going to get used to seeing this. I like to refer to it as del squared. But again, nabla, Laplacian, del are all appropriate names for that operator. Okay, so now this is where this does get a bit nasty at first. As you see where this is going, because we need to transform our xy space into r theta phi space. So for now, this is not so bad at all, because for one, r is constant. Okay, so we're just going to allow for one single radius. We're not going to allow for the particle to move in and out of the origin. We're just going to say it's fixed at one radius, spinning right round, baby, right round. Okay, and we're also going to be ignoring theta. So we'll say theta, we're not going to worry about it, right? Because remember, theta goes in this dimension. We'll eventually have to think about the theta dimension when we turn this into particle on a sphere. But for now, the only thing that we actually care about is the partial in phi. And here's why, okay? So through standard manipulation using these relationships, that the sine of phi is r divided by y, and the cosine of phi is x divided by r. So this is from SOHCAHTOA, right? Then the two-dimensional del squared, right, in x and y, that becomes the second derivative in r squared plus 1 over r times the first derivative partial in r plus 1 over r squared times second derivative in phi. So I'm not going to hold you responsible for doing that manipulation because it is a standard coordinate transformation. And it at first looks like really nasty, right? Like, what are we going to do with all these things? However, because r is constant, we don't care about any of the derivatives of r. Okay? So this goes away. And this goes away. Which means also that 1 over r term that's in front of that derivative goes away because the derivative is 0, given that r is constant. Okay? So now, look, this is the only thing that we have to worry about for our Laplacian, or for del. Okay? So now, check this out. Our kinetic energy Hamiltonian operator, right, becomes negative h bar squared divided by 2m, so there's still that part. But now we just replace it with the 1 over r squared partial second derivative in phi, which I get right here. And look how sweet and easy that becomes, right? We know mr squared is just moment of inertia I, and I replace the partials with d's because now we only have one single dimension to deal with, okay? And it looks exactly like our kinetic energy operator for translational motion, which is great. Okay, so continuing along with this thing. Let me check the time. Okay, 20 minutes. We're doing great. So now my Schrodinger equation, h psi equals e psi, becomes very simple. So my operator now is just negative h bar squared divided by 2I times partial derivative, second derivative in psi equals e psi. Okay? So let's do this thing. We can solve this all day long. Cry, pray, guess, solve. We can do this. And that's what we're going to do right now. So let's go for it. Okay? So here I have my Schrodinger equation. And the first thing that I want to do is get that in the standard reduced form. Okay? So I'm going to just do that algebra right here, right? I'm going to multiply negative 2I over h bar squared through. Okay, so I get second derivative in phi of psi. And now that equals negative 2IE over h bar squared times psi. Okay, and putting that into our standard form, where I set the right side equal to 0, that becomes plus 2IE over h bar squared times psi equals 0. This is a very easy, straightforward second order differential equation to solve. Okay, we're going to guess, right, that psi equals e to the a phi. I know it's tempting to say e to the ax, but remember phi is our variable. And so now I'll just go very quickly to the second derivative directly, right? We know that that's going to be a squared e to the a phi. So this is all looking very familiar and all good. And so then when I plug that into this whole thing, right, I get now a squared e a phi plus 2IE divided by h bar squared. And then now times psi, which we guessed is e to the a phi, all equals 0. So we know that we can eliminate the e to the a phi. And so that's going to give me a squared plus 2IE divided by h bar squared, all equals 0. And I think you can see where this is going. We're going to get imaginary roots, right? So this is going to be now a equals negative 2IE divided by h bar squared, all square root. And so now I'm going to use some other foreshadowing here. I'm going to use a different letter than a. Okay. So, excuse me, I'm going to say now that a equals I times m sub l. Why am I going to use m sub l? Well, because actually, as it turns out, look at this. This is really cool. So now we know that this ml right here, okay, equals the square root of 2IE divided by h bar squared. So how did I know to use that ml? Well, let's back up for 1 second. Aha! Right? E equals ml squared times h bar squared divided by 2I. Well, what if I rearrange this? Let's do that. So I multiplied both sides by 2I. So I've got 2IE. And now I'm going to divide both sides by h bar squared and take the square root. That gives me quantum number ml, which is really, really cool that we know that it's a quantum number. It's got to take on only integer values that we've seen, plus minus 1, plus minus 2. But the fact that it's also equal to the square root of 2 times the moment of inertia times the energy divided by h bar squared, all square root, and that this, in fact, will equal plus or minus 1, plus or minus 2, etc. That's pretty cool, I think. Okay. And so now, when we go, let's see.